In this video, we discuss about modeling with systems of ordinary differential equations. This is useful in situations where we want to capture more than one variable. Very often, models must describe interactive situations. Several variables are involved, their change depends on all the other variables. For example, an animal may serve as prey for another, two species may depend on each other for mutual support, two or more species may compete for the same resource. So in this case, we will model the situation through a system of differential equations. Each equation gives the rate of change of one variable as a function of the current values of all variables. And we will solve all equations simultaneously. Now, here is some bad news. The equations that we get in this way are often non-linear, and in general they cannot be solved analytically. There is also some good news. There are many numerical techniques to analyze the behavior of such systems of equations. In this video, we only consider autonomous systems of ODEs. In other words, there is no independent variable t on the right-hand side, meaning that the system is not time-dependent and it only depends on the variation of its variables. A notion of equilibrium point or a steady state exists also in this case, and it's similar to that where we had only one unknown and one equation. The intuition is the same. An equilibrium point is one that makes all the functions on the right-hand side of our system of ODEs to be zero. In other words, starting from an equilibrium point will give us no fluctuation, and so all the variables will remain constant. The stability of equilibrium points is defined in a similar way as for a single variable. Intuitively, a point A is going to be called stable if it's true that x of 0 being close to A implies that x of t is going to be close to A for all t larger than 0. A is going to be called unstable otherwise. Also, asymptotically stable, we will say that A is such an equilibrium point if it's true that x0 being close to A implies that eventually x of t is going to converge towards A. Here is an example. Let's assume that we have a small pond that we desire to stock with game fish, let's say trout and bass. The problem we want to solve is whether it's possible for the two species to coexist. And here are the hypotheses of our model. There is an unlimited amount of food available, and the space is a limitation for the coexistence of the two species. So this means that the more there is of the other species, the smaller the growth rate is going to be. And there could be several cases, but let's assume that the cause for this in our model is going to be competition for space, and we will model it as proportional in the number of possible interactions between the two species. So the model formulation is going to be like this. The change in the level of trout, let's say x of t, so the change is dx to dt, is going to be like this. On one hand, we have a growth rate, and that will give us the term a times x of t. And then we have the effect of these interactions between the two species is, and that we will model as being x of t times y of t with some proportionality constant b in front of this term. A similar reasoning also for the level of bass, y of t. dy to dt is the growth factor m times y of t minus x of t times y of t multiplied also with some proportionality constant n. So the model we have is dx to dt equals a times x minus b times xy, and dy to dt is m times y minus n times x of y. And so the question is going to be, can the two populations reach an equilibrium where both are zero? To answer the question, it's enough to find the points where the functions on the right-hand side of the two equations are zero. So, in other words, we have to solve ax minus bxy equal to 0 and my minus n times xy equals to 0. And there are two solutions. One solution is x equals y equals 0, and the other solution is x is m over n and y is A over B. So here is the difficulty. It's impossible to start with exactly the equilibrium values because they might not even be integers. So if we want to start with m over n and y a over b, that's going to imply some practical difficulty. And so since we cannot expect to start exactly in the equilibrium point, we will aim to start somewhere close to it. And we will have to study now the property of this equilibrium point and hoping that it's a stable one, meaning that even though we don't start exactly in the equilibrium point, the situation that we will get is a stable one where we have both species coexisting in the pond. To answer the question, we look at whether x and y increase around the equilibrium point m over n, a over b. And for this we are going to study the derivatives of x of t and y of t. So we look at this question, where is dx to dt greater than or equal to 0? And this is equivalent with ax minus bxy greater than or equal to 0. And this is equivalent with a over b is greater than or equal to y. So what this means is that we have this, and if this is the value a over b, we have a growth in the level of x if we have a value of y here, and we have a decrease in the value of x if we have values of y here. The similar question for y is solved by looking at this inequality dy to dt greater than or equal to 0, and that can be written as m times y minus n xy greater than or equal to 0, and that's equivalent with m over n is greater than or equal to x. So y is going to increase whenever x is under this value. And we can see this in this graphical way. If this is value m over n, whenever x is in this side, we will have an increase in the level of y, and whenever x is on this side, we will have a decrease in the level of y. And so if we put these two together, I'm going to just copy these plots together on this side. This is y and this is x, and let's say this is a over b, and let's say that this is m over n, and the growth was like that on this side and like this on this side, and it was like this on this side and like that on this side. So what this plot is suggesting is that if you start from a point somewhere here, then these two arrows combined mean that you are going to be pushed further and further away, and in fact in this situation this population y eventually is going to be going to 0, so x is winning. The same situation here, if you start somewhere here in this part of the plane, these two forces combined mean that you are going to be pushed in that direction, meaning that the x population is eventually going to be driven to 0 and the y population is going to just dominate the whole pond. So again, you don't have the two species coexisting, y is going to win over x. Now if you start here, there are these two forces combined, and it really depends which one is stronger. There is a chance that maybe this one is stronger, and then you are going to be eventually pushed upwards and then further away, or you are going to be pushed downwards and you are going to be pushed further away in this direction. And the same thing here, if you start with in a point here, there are these two forces, and depending on which one wins, you are going to be pushed either in this quadrant and then further away in that direction, or you're going to be pushed in this quadrant and then further away in this direction. So overall, we get that there is a fine line in this model as shown in this plot. If we start with some value above the line, the bass wins, meaning that the trout will eventually disappear from the lake. If we start below the line, then trout wins, meaning that the bass will eventually disappear from the lake. So the conclusion is that, according to this model, it's very unlikely that we can ever have the two species coexist in a lake.